For the electrolytes and ionic reactions lab activity, we're going to be working with electrolytes, strong, weak, and non-electrolytes, as well as writing out the precipitation reactions and acid-base reactions, and looking at net ionic reactions and so forth. So in our introduction, we are reminded that water is polar. It has a partial negative end and a partial positive end. Remember that Greek symbol delta we use to indicate just a portion of a negative or a portion of a positive. Due to the polarity of water, it can dissolve many ionic compounds. It dissolves sodium chloride, where the oxygen end, the partial negative end of water, likes the Na plus, and the partial positive end, the hydrogen end, likes the chloride ion. And as we went over in the chapter 4 handout and the video, that causes sodium chloride to dissolve in water. And that process is dissociation, where the sodium chloride fully becomes separated ions in solution. And we can write out that reaction as is shown in equation 1, NaCl solid dissolving in water to form Na plus aqueous plus Cl minus aqueous. Ethanol, which is CH3CH2OH, ethanol is soluble in water. You probably know that from experience. Beer, wine, hard drinks, those all contain ethanol, and we don't have two separate layers. We don't have that oil vinegar two separate layers that we get in typical salad dressing. Rather, we have just one consistent homogeneous solution. So the ethanol is fully dissolved despite the fact that it's a molecule. It's not an ionic compound. Remember that ionic compounds you would recognize as such. They are composed of cations and anions. When you see a formula like CH3, CH2OH, you don't see cations and anions. So you know that that's not ionic. But it is soluble in water due to the OH. The OH is kind of like the OH in water. The O has a partial negative charge, the H has a partial positive charge. The H of ethanol likes the O of water, the O of ethanol likes the H of water, so it fully dissolves. And we see that reaction as CH3, CH2OH liquid in water forming CH3, CH2OH aqueous. So remember that the difference between liquid and aqueous is significant. Liquid means it's all together, and then aqueous means each molecule is surrounded by water. It's different, however, than the ionic reaction because ethanol never becomes an ion. Yes, it dissolves in water, it forms an aqueous solution, but it does not form ions. So I was talking there about reaction 2. Electrolytes are substances that dissolve in water, and if they are strong electrolytes, they form ions 100%. If we dissolve 100 NaCl's in water, they will form 100 sodiums and 100 chloride ions. That's a strong electrolyte. Non-electrolytes are like the ethanol, CH3CH2OH. Yes, they dissolve in water, but they do not become ions, so they're non-electrolytes. We also have weak electrolytes, and they are typically weak acids and bases where they do mix with water, they form aqueous solutions, but they mostly stay together as the original molecule, but some of them do separate into ions. HF is an acid. It's not one of the acids that's a strong acid. There were 6 of them from our chapter 4 notes that you would recognize as strong acids. HF is not one of them, So yes, it's an acid, but it's not strong, so it must be a weak one. That means when we dissolve it in water, we get a little bit of H plus, a little bit of H minus, but the bulk of it exists as HF, just surrounded by water, kind of like how the ethanol dissolves. So that would be a weak electrolyte. Electrolytes, strong ones and weak ones, conduct electricity, but the weak ones would conduct it not as well. If we had that light bulb demo, the light bulb would glow, but it would be very dim. For the KCl, the light bulb would be bright, and for the ethanol, there would be no glow whatsoever. So, writing chemical equations. One of those is represented by reaction equation 3, and that is the calcium nitrate plus sodium carbonate. We exchange partners. We put the calcium with the carbonate and the sodium with the nitrate. And if we look at the solubility rules that are in chapter 4 in our handout, in the video, we would see that carbonate compounds form solids with cations, and except for the alkali metals, the group 1A. So calcium is not from that group, so it forms a solid with the carbonate. So we get calcium carbonate solid, and sodium nitrate is aqueous according to our solubility rules, so we indicate that with the AQ. Notice that on the left side, on the reactant side, everything's aqueous, and we need to, of course, include those subscripts on the product side, so that's why we have the solid and the aqueous. And then we balance the reaction. 2 sodiums on the left, so we put a big 2 in front of NaNO3 on the right. Also notice that we have written the products as neutral compounds, Na plus, NO3 minus, so they're on a 1-to-1 ratio. Ca2 plus, CO3 2 minus, so they're also on a 1-to-1 ratio. The complete net ionic equation, that would be where we separate everything that's aqueous. So we have Ca2 plus aqueous, plus 2 NO3 minus aqueous, plus 2 Na plus aqueous, plus CO3 2 minus aqueous, because they're all separate ions right before the reaction occurs. The calcium carbonate solid, those are together, those ions, so we indicate that. And we have the 2 Na plus aqueous plus 2 NO3 minus aqueous. For the net ionic equation, whatever is the same on both sides, we don't show. So in equation 5, we have the NO3 minus the same on both sides. The 2 of them, we have the 2 Na pluses the same on both sides. The slash lines on the product side, those should have been shifted a little bit. The slash line should be over the 2 Na plus aqueous and the 2 NO3 minus aqueous. So we eliminate those from the net ionic reaction because they remain the same on both sides, and we have reaction 6, Ca2 plus aqueous plus CO3 2 minus aqueous, forming CaCO3 solid. Okay, you can ignore the pre-activity and move into the report, which of course you will do and submit. So our first problem here is to indicate the major components present in the aqueous solutions of the following. So that is, you write 2K plus, SO4 2 minus, and so forth. We have a molecule in there, the C6H12O6. You hopefully recognize that that is not an ionic compound, so it must be a molecule. And yes, that actually does dissolve. That would be an example of glucose or fructose. They both have that molecular formula. They will dissolve in water, but they will not separate into ions. In problem number 2, we have all soluble solutions, and they all have the same molarity, And what we're to show in the beaker representation is the ratio of the calcium to the chloride ions, the sodium to the chloride ions, the aluminum to the chloride ions. And they're not the same. NaCl 1 to 1, CaCl2 1 to 2. So draw your picture accordingly. And problem number 3 has you deciding which would be the most conductive, which has the most ions. In problem 4, we're also drawing the beaker representation. Now you have to think about whether the ionic compounds that are shown there are going to be soluble or not. So, and we have a few acids as well. The HCl, the HNO2, those are both acids. Think about whether they're strong acids or weak acids. That will matter in how you draw your picture. Weak acids, the bulk of them do not separate into the H plus and the anion. They stay together as a molecule. So keep that in mind in your picture. For the ions, as we talked about, make sure that you check the solubility rules. If they are insoluble, then you would just show them as the cation together with the anion. We also have 2 molecules, methanol and ethylene glycol. Methanol is soluble in water just as ethanol is, but it's a molecule. Ethylene glycol is the material in antifreeze, and that also makes for a solution. We don't have 2 layers, so that means ethylene glycol is soluble in water, but it's also a molecule. Keep that in mind. Okay, now we're writing out the equations. So for problem number 5, we do the exchanging of partners one. We look at the solubility rules to see if solids form. So we indicate the state of the aqueous, the solid states of the products. We balance the reaction. We make all the compounds neutral. Number 6, we are told that we are working with aqueous solutions of strontium chloride, so we'll have to write out what that is, make it neutral, and lithium phosphate, write that out, of course, make it neutral, and then you'll do the exchanging of partners, and you'll check out the solubility rules to see if a solid forms, aqueous solutions form. You will then balance the reaction and indicate aqueous, of course, for the reactants because we're told we're starting with aqueous solutions. And then write out the complete ionic equation, kind of like the beaker representation, and then cancel out any ions that appear the same on both sides and write out the net ionic equation. Don't forget all the aqueous and solid notation needed. In the net ionic equation, you're going to show charges of the reactants because you are leaving off their counter ion. Number 7, we have a similar kind of problem as we had in number 6, but it's an acid-base reaction, but we're doing that still exchanging partners. Acetic acid, that's not one of the strong acids, so that means that it stays together for the most part. Potassium hydroxide is a strong base. So bear all that in mind as you write out those molecular or formula equation, net ionic, and then the complete ionic equation. Number 8, we are writing out just the net ionic equations, but you probably will, on scratch paper, do the full reaction where you're exchanging partners, making everything neutral, balancing, etc. Checking out your solubility rules for what is the notation for the products, aqueous or solid. And you're just, though, then you're canceling out ions that appear on both sides to be able to write out the net ionic equation. And for, let's see, reaction A, we have just a precipitation type reaction. B is an acid-base type reaction. C, again, a precipitation reaction. D is an acid-base reaction where HCHO2 is an acid, but it's not one of the strong ones, therefore it must be a weak one. Take that into account as you write out the net ionic reaction. And I strongly urge you to go back through the chapter 4 handout, very much making sure that you understand the difference between the strong and weak acids and the significance of that in the net ionic reaction. And then we have question number 9. HCl conducts electricity in water, but does not conduct electricity in a solution of chloroform. And you're asked to think about what's going on so that it won't conduct electricity in the chloroform. Remember, to conduct electricity, we have to have mobile ions. Alrighty, so when you're done with all of those problems, double check, make sure you have everything you want there, then do the scan PDF file and submit it.